what I'm going to be talking about today is something about objects that we called Freiman multi-homomorphisms. So everything that I talk about today is joint work with Tim Gowers. All right, so let's start off with an easy sort of introduction. And the first thing that I would like to mention is classical Freiman's theorem. And so let's recall what Freiman says. So if you're given a finite set of integers such that you don't get too many sums, so if you have a set with small doubling, namely all sums of, you count all sums of pairs, and if that quantity is not much larger than the size of A, then you can conclude that actually A is contained in something called generalized arithmetic progression of dimension bounded by this constant K that we had in the condition on A, and the size of this generalized arithmetic progression is also not much bigger than A. All right, so just to be perfectly clear, what I mean by generalized arithmetic progression of dimension D is just sum of D arithmetic progressions in the usual sense. That's all right. I won't actually be interested in integers in this talk. I'll actually be interested in the setting of vector spaces. So let's fix a prime field FP. So we're just interested in prime fields. If you had a field which was of order, for example, P squared, that doesn't play very much a strong role here because we're actually interested in additive structure only. So imagine that we have a fixed field FP. And whenever I say a vector space, what you really mean is finite dimensional vector space over FP, but that's a bit mouthful, so I'll just abbreviate that to vector space. All right, so what does Freiman's theorem become in the setting of vector spaces? Well, it becomes actually slightly neater. And it says the following. Once again, if you have a set A with small doubling, so there are not too many sums in A, you can conclude that A is actually contained in a coset of a subspace this time, and that this coset is actually not much larger than A. Once again, how much larger than A depends on this constant K here. Okay, so now we're going to have a look at Freiman homomorphisms, which are actually an important class of maps which play significant role in proof of Freiman's theorem. So when I say Freiman homomorphism, what do I mean? I mean, first of all, let's fix some vector spaces G and H, and let's consider a subset of G. Let's call it A, and we think of A as a dense subset of G. And we say that a map from A to H is a Freiman homomorphism if it satisfies this condition here. So on the left-hand side, we have a quadruple of elements in A, which satisfy A plus B equals C plus D. We call such quadruples additive quadruples. And what happens with Freiman homomorphism is that whenever you have this additive quadruple like this here, then you also get that phi of A plus phi of B is equal to phi of C plus phi of D. So we typically say that phi respects additive quadruple A, B, C, D if this holds. So in other words, Freiman homomorphisms are maps which respect all additive quadruples in their domain. And we can think about these maps as being approximately linear, or better, is better to say maybe approximately affine, because if it happens that A is actually the full space G, then this property here of respecting additive quadruples actually becomes the defining property of affine map, where by affine map I really mean linear map plus a constant. And actually, one can justify this connection with affine maps more formally by means of the following theorem. So suppose once again that phi is defined on a dense subset of G, and it maps to another vector space H. And let's be slightly more general and say that instead of phi respecting every single additive quadruple in A, phi respects a positive proportion of all additive quadruples in G. So it's a slightly more general condition, but it's all these maps are essentially the same anyway, as this theorem will show. So in this set, in this case, we can actually conclude that phi necessarily coincides with a global affine map. So when I say global, I always mean that the domain is the full space in which one lives. So we get an affine map, big phi, from the whole vector space G to vector space H, such that big phi equals small phi for many elements inside A. So this justifies being approximately affine. So whenever you have a map which is approximately affine in the sense that you respect many additive quadruples, you actually come from global affine map. All right, so now I would like to just give a sketch of this proof as we are still warming up. So what happens in the proof? Well, the first step is actually to consider the graph of phi. So namely, you just take a look at all possible pairs where one element is just element of your set, of your domain, and the second element is its image under phi. And then one can think about what this condition of phi respecting many additive quadruples means. Well, it exactly means that gamma has high additive energy, meaning if you pick 3 elements, x, y, and z from gamma at random, then with positive probability x plus y minus z belongs to gamma. And then once one sees high additive energy, so when we see that condition, we immediately think of Bogolyubov theorem. And we are able to find a large subset gamma prime inside gamma, which has now small doubling. So exact condition from Freiman's theorem, and thus we apply Freiman's theorem, which gives us a further coset C, which is not much larger than gamma prime. And then we just need to see what coset C means in this new scenario where we actually look graph of gamma. So if we return now to our original viewpoint, where we actually looked at maps from G to H, it turns out that cosets on the graph side of on the graph viewpoint corresponds to affine maps in the initial viewpoint. So I'm saying here essentially that C essentially corresponds to an affine map because there is an issue that the projection from C onto the first coordinate might need not be injected, but that's a minor point. Anyway, so I was deliberately quick here and maybe skipping some details. But my point was really, you can prove this theorem about Freiman homomorphisms and more general maps which respect many additive quadruples. You can prove such theorem easily using Freiman's theorem, although we did use Bogolyubov theorem as an ingredient, but let's pretend that that wasn't the case. But anyway, and on the other hand, you can actually easily prove Freiman's theorem from this inverse theorem for Freiman homomorphisms. So, and this time, when I say easy, I really mean easy. You don't need additional ingredients like Bogolyubov theorem. So the reason why I mention all this is that actually there is a very close connection between Freiman's theorem and this variant of Freiman's theorem for maps that respect many additive quadruples. So basically you can see them almost as the same theorem. So that means that it makes sense to study Freiman homomorphisms and to try to generalize this notion to higher dimensions. And that's exactly what I'm going to be talking next about. So my next topic, and the first proper topic today, is actually how to generalize the notion of Freiman homomorphism to higher dimensions. And when I say higher dimensions, I really mean more variables or higher arity, not dimension in the sense of dimensional vector space. So, okay, so let's give it a try. Let's fix some vector spaces, G1 up to Gk, which will serve us as the domain of our function. And H will again be the target space. And let's have a dense subset of G of product of G's. So actually we are taking a dense collection of K tuples where ith element belongs to ith vector space. And then we are considering a map phi from A to H. And now we want to say that phi is a Freiman multi-homomorphism if phi is essentially usual Freiman homomorphism when restricted on lines in each principal direction. So let's be precise and go into details of this definition. So we fix, so for any D, which is among 1 up to K, for each coordinate except coordinate corresponding to vector space GD, we fix one value. So we fix x1 in G1 all the way to xd minus 1 in GD minus 1. Then we fix xd plus 1 in GD plus 1 and xk in GK. And we consider the induced map on line in direction D. So we send yd to the phi value of the corresponding K tuple, which is given by putting yd at this place and leaving x's at other places. And thus we require that these induced maps are Freiman homomorphisms. So just to be clear here, I didn't specify the domain of this induced function, but it's the reasonable thing. So you simply take all possible YDs such that the K tuple that you get lives inside A, so that the phi value is simply defined at the K tuple. All right, so so what happens, once again, we should ask ourselves what happens in the case that we are lucky and A is actually the full product of G1 up to GK. So in that case, we once again get the defining property of multi-affine maps. So in other words, global Freiman multi-homomorphisms are exactly multi-affine maps. And if you're not used to thinking about multi-affine maps, well, let me just be clear and say that these are just sums of multilinear maps. So for example, in the case of two variables, a general bi-affine map would be given as a sum of a bilinear map alpha. Then maybe you would like another linear map, but involving just x as a variable, another linear map involving just y as a variable, and a constant c. So, but if this sounds maybe overwhelming, you can think about multilinear maps as a good first approximation here. All right, so let me just clear drawings and proceed. Okay, so we've defined Freiman multi-homomorphisms and we've indicated what global Freiman multi-homomorphisms are. And now we're ready to state our main results. So this is a theorem Tim and I proved this year. And it essentially says, well, Freiman multi-homomorphisms come from the thing you hope they come from, namely they come from global multi-affine maps. So once again, let A be a dense subset of this product G1 up to GK. Let phi from A to H be a Freiman multi-homomorphism. And then one can conclude that there is a global multi-affine map big phi. So its domain is actually the full product. And little phi and big phi coincide on a rather dense set. So we actually can give explicit bounds for the density of the set where these two maps coincide, and the bounds are reasonable. So here we have a tower of exponentials of bounded height. And here we have, of course, delta inverse, and we take the inverse of all that. So I should say that this height can actually be also controlled. So it roughly grows like k factorial, let's put it that way. But the point is actually we get primitive recursive bounds. So they do not explode as k grows. All right, so this is our main result. And I should first say something about related results. So
what is P?
Sorry, P is a prime that you've fixed. So you have some,
right, yes.
some little annoying dependence on P, but P doesn't play a role in the tower height. So,
okay.
So it's just something like you would like to take logarithm with base P sometimes, but you can't. You can only take logarithm with base 2 or something like that. But it doesn't play a huge role. So I was just pedantic here, but anyway, the main thing that you're interested in is the height of this exponential tower, and that's roughly k factorial. It doesn't have P playing any role. Okay, but anyway, thanks for asking. So let's mention some related results. So the first result I would like to mention is actually another result from Tim and myself from 3 years ago, where we actually proved an inverse theorem for bi-homomorphisms, which is the case k equals 2 above. And we obtained a similar kind of bound. So we also got a tower of exponentials, and I think it was tower of height 2. But another result, which I would really like to stress, is results from 2 years ago, when Freddie Manners proved an inverse theorem for approximate polynomials in cyclic groups with good quantitative bounds, and this was really a major breakthrough. So here, maybe I should stop for a moment and just indicate what these approximate polynomials are. We won't be talking about approximate polynomials here, but we will be talking actually about uniformity norms. So it's actually a good warm-up for uniformity norms later. So suppose that you actually had some function f on your group, maybe 2 complex numbers, or actually better, to another group in his case. And then you can consider discrete derivative, which is just an operator which makes a new function from your initial function. And it's just looking at f, and then you take difference a here. So why it's called discrete derivative? Well, it resembles derivative closely, and it has similar properties. So why is this useful? Well, for example, if you take a double derivative of f at x, what you get is, first of all, you apply derivative with difference b, and that gives you f of x minus b. And then you apply another derivative, which will produce more terms. And you get this thing here. So one can actually think about this as an additive square, because here you move by b, and here you move by b, or maybe additive rectangle, here you move by n, here you move by a. But another way to view this is actually you get actually an additive quadruple. So if the second derivative turns out to be 0 frequently, that exactly means that your function actually respects many additive quadruples. So that's the thing we've seen before. So if you respect many additive quadruples, you're actually approximately linear. And then one can ask the question, what happens if your function respects higher order derivatives? So for example, you had 4 derivatives here, and you get zeros frequently, and then you can actually conclude that your function is approximately cubic polynomial. So what Manners proved is that he gave structure theorem for approximate polynomials, meaning functions that have their higher order derivatives vanishing a lot of the time. Okay, so that's what I wanted to say about approximate polynomials. And now I should probably say something about how is our new result, how it can be compared to Manners' result about approximate polynomials. So firstly, in the most general sense, we have proofs of similar spirit, but the details are quite different because he works in cyclic groups and we work in vector spaces. And for example, one important thing about our work, which prevents us from generalizing to cyclic groups, is that we rely very heavily on the solution to analytic versus partition rank problem. And that problem has not been properly described in case of cyclic groups. And on the other hand, what Manners does, he has some essential assumptions that the groups for which his proof works need to be of bounded rank and have no small subgroups. It's exactly the opposite situation from ours. And there is one further thing, and that's that one can actually conclude relatively straightforwardly an inverse theorem for approximate polynomials from our inverse theorem for Freiman multi-homomorphisms, but the other conclusion is not clear. It's not clear whether you can use inverse theorem for approximate polynomials to deduce inverse theorem for Freiman multi-homomorphisms. But let's stop there. And before proceeding to talk about the applications of our theorem, I want to stop briefly and make a slight digression and talk about partition versus analytic rank problem, because it plays a huge role in our proof. So the main question here is the following. So suppose that you have a multilinear form alpha in k variables. And of course, when I say form, that just means that the codomain is just the field itself. So when is such a form quasi-random? And one obvious definition of being quasi-random when it comes to multilinear forms is just saying, well, the distribution of values you get is roughly uniform. And if you think about it, so for example, if you fixed first k coordinates, so imagine that x1, first k minus 1 coordinates. So these are fixed, and then you leave the last coordinate to vary. So for any choice of x's, what you get is just a linear form from gk to fp. And we actually understand linear forms perfectly. So those forms are either zero as zero map, or they're surjective maps. So that means immediately that for any choice of x's here, you get 0 all the time, or you get 0, 1 up to p minus 1 equal number of times. So what we conclude from this is actually the distribution of values is as follows. So 0 is the most frequent value, and the other values are actually equally frequent. So we have some, so the distribution cannot be completely arbitrary. Okay, so that means that actually we can control the distribution by single number. And this number is usually called bias. So bias of alpha is just the expectation of the phase function of your multilinear form. And now, on the other hand, we may think about, and okay, let's just say explicitly, well, bias is small. So let's put it this way. If your distribution is uniform, bias is small and vice versa. All right, so now we can think about the abstractions to being quasi-random, or in other words, can we find an example of alpha such that this bias is large? And there is a very simple example. So imagine that you have a map alpha which splits as a product of two further multilinear maps. So imagine that beta is arbitrary multilinear map in first L variables, and gamma is a multilinear form in the remaining variables. And then if you think about it, whatever I pick for x1, whenever beta is 0, whatever I pick for the remaining variables, I get 0 product still. And then you can just plug those informations in the bias above and do a simple calculation to get that bias of such a map is necessarily at least 1 over p. So it's huge. It's actually bounded away from 0 by a constant. And what's interesting here is actually that such maps are the only kind of abstraction to being quasi-random. So we have the following theorem. This has a history. So first of all, in a qualitative sense, before I say what this theorem actually says, let me just mention some names. In a qualitative sense, this was first proved in 2015 by Baumek and Lovett, who were building up on previous work by Green and Tao, who in 2008 proved a similar result for polynomials instead of multilinear forms. And the result below is actually a result from Jonzer and myself independently from last year. So what happens here is, suppose that you have large bias, let's say at least C. Then you can conclude that alpha is actually a sum of very few forms of this form, forms of this shape, let's put it that way. So forms that split as products of two further forms. So, and the point here is actually we have very good bound on the number of forms here. So it's actually just a polynomial in the logarithm of C inverse. And the previous bounds were, so they weren't primitive recursive because they depended on regularity lemmas. There was an intermediate result of Jonzer a year before this where he had a double exponential, I think. But anyway, so here we have near perfect bounds. And it is this theorem which allows us to evade use of regularity lemmas in our work on inverse inverse theorem for prime and multi-homomorphisms. All right, so now that I've mentioned this problem as well, I'm ready to speak a bit about applications. Okay, so first application that you have in mind is application to the theory of uniformity norms. And for this, I would like to remind you of the definition of uniformity norms. So these were introduced by Tim in his work on Semiredis theorem. So this is the formal definition. And if you see it for the first time, it's a bit, well, hard to understand probably, but what happens here is you get similar expressions to the expressions I mentioned in the discussion of approximate polynomials. So what you do is, for example, in the case k equals 2, the order 2 uniformity norm is given by taking the expectation over products of this shape. So these were exactly the additive squares or additive quadruples we had before. If you had order 3 here, you would take expectation over products of 8 things. You would introduce another round of taking differences with C here. So you take x minus c, you take x minus a, you subtract c from x minus b, you subtract c from x minus a minus b. And then for 4 variables, you would get then 16 terms, etc. So that's what happens on the right-hand side. There is this conjugation operator term, which means that you actually conjugate all those things with odd number of differences taken. But okay, let me put this here, but that's of minor importance. I mean, it has importance, but it's this is the structure of points that you're taking as arguments of f is what you really need to understand here. All right, so what's the point of these norms? Well, if your function has, let's say, small value of a uniformity norm of order, let me just get back, okay. So if your function has small value of uniformity norm of order k, that essentially means that f behaves quasi-randomly on objects of complexity k minus 2, whatever that means. But for example, in the case of arithmetic progressions, you can think about arithmetic progression of order of length k as having complexity k minus 2. So if you have small uniformity norms, you can count arithmetic progressions efficiently, essentially. So in Tim's proof of Semiredis theorem, what we have to do is actually to understand functions that have large uniformity norms. So that's essentially the main goal. And this is, so theorems that say something about the structure of such functions are called the inverse theorems for uniformity norms. And first such result was, of course, proved by Tim himself when he proved Semiredis theorem. So in the case of cyclic groups, he obtained local correlation with polynomial phase function. So what I mean by local correlation here, well, it means that your function has large inner product with polynomial phase on a relatively long arithmetic progression, where relatively long means a positive power of n. And after this result, people started wondering if they can obtain a global correlation. So can you prove a theorem which says you have correlation on the whole group with certain structured function? And here we have several remarkable important results. So first result that I would like to mention is a result of Bergelson, Tau, and Ziegler from 2010, which was further refined by Tau and Ziegler in 2012, who proved a strong inverse theorem in the case of vector spaces. Namely, they obtained global correlation with phases of something they called generalized polynomials. So I won't be able to say what these generalized polynomials are exactly today, but let's just mention that in certain settings where, for example, if P is large enough, these generalized polynomials become just usual polynomials. So next important and remarkable result that I would like to mention is results of Green, Tau, and Ziegler from 2012, who proved a strong inverse theorem in the case of cyclic groups, and they obtained the global correlation with objects called Neal sequences. So these are polynomial sequences on Neal manifolds. And there is further work. So there is, for example, a more abstract approach to inverse theorems, namely theory of Neal spaces, initiated by Szegedy and studied by Antolin Kamaran and Szegedy together, and with further refinements and generalizations by Candela and by Gutman, Manners, and March. All right, so all these things that we mentioned did not provide essentially any bounds in this problem. They didn't give explicit bounds on the correlation. So one can, and that's because they either used infinitary methods or they use regularity lemmas. So now we proceed to think about what is known about quantitative versions of these theorems. So first of all, in general, abelian group G, in the case of U3 norm, good bounds were given by Green and Tau in 2008. And then what I would like to mention is the result of Manners from 2018. So this was the major breakthrough that I mentioned before. He used his inverse theorem for approximate polynomials to deduce quantitative version of inverse theorem for uniformity norms. So once again, he obtains a double exponential bound here. And then in the case of vector spaces, apart from U3 norm given by Green and Tau, there is a quantitative inverse theorem for U4 norm given by Tim and myself in 2017. And that is what we proved actually the inverse theorem for Freiman by homomorphisms, which I mentioned previously. So this is our second main result and the main application of our inverse theorem for multi-homomorphisms, namely a quantitative inverse theorem for uniformity norms in the case of vector spaces and in the case of high characteristics. So when I say high characteristic, that means that prime is at least the order for your norm, namely K. So if you have large uniformity norm, you can find polynomial in the usual sense of the word, degree at most k-1, such that your correlation here is at least the inverse of a tower of bounded heights. And these heights are the same heights we had in the inverse theorem for prime and multi-homomorphisms. So once again, these bounds are reasonable and they are primitive recursive. So they do not explode as k grows. All right, so let me now give a sketch of how Freiman homomorphisms come into play in the proof of inverse theorem for uniformity norms. So for this, let's properly introduce discrete derivative notation. This is a multiplicative derivative because we are taking products here instead of differences. So you fix A, which is your difference, and then derivative with difference A of f is just f of x times conjugate of f of x minus A. So as I mentioned already, if you look at the definition of uniformity norm, you can express it much more neatly using this derivative notation. So once again, you take expectation over all parameters, so expectation over x and over size of your additive cubes a1 up to ak. And then you just end up with this thing, which is actually just have, this exactly makes an additive cube with base point x with sides a1, a2 up to ak. And then one can play the same game in just the last two parameters, ak minus 1 and ak. So we can, if we fix a1 up to ak minus 2, what we get here would be an expectation over x, ak minus 1, and ak. And that would be just the definition of U2 norm raised to power 4, actually. And once you have U2 norm, U2 norm is actually very easy to understand. And that's why I actually didn't mention U2 norm in previous results. So U2 norm raised to power 4 is exactly the sum of 4th powers of modulus of Fourier coefficients. So you get an expression like this. And then you do the usual thing, namely you apply Parseval's identity to conclude that actually you can bound such sums by biggest Fourier coefficient raised to a square, right? Okay, so we get an equality like this. And then you can simply pick those k minus 2 tuples a1 up to ak minus 2 such that the right-hand side is reasonably large. So by usual averaging arguments, that means that you have dense collection of such k minus 2 tuples where the right-hand side is large, and you pick then for each such k minus 2 tuple, you pick the relevant r. So what we end up is the following. So we get an auxiliary map phi defined on a dense subset of k minus 2 tuples with the following properties. So whenever you have a1 up to ak minus 2 in A, you have large Fourier coefficient here. So this is your function, and phi of a1 up to ak minus 2 is the large Fourier coefficient of this function. So this is the crucial property, and let me rewrite it once again to see it clearly. So now we just focus on this property only. And this property already implies that phi respects many additive quadruples in each direction. So once you have this property so once again, what do I mean in each direction? I really mean in each principal direction. So you fix direction D, you fix all other coordinates, and then you count additive quadruples that are respected on lines in direction D. And then we can apply our variant of Freiman's theorem for approximately affine functions to conclude that actually you can restrict phi on a dense subset such that in direction D, for example, phi coincides with global affine map on each line. But we don't need such a strong property. We just need that we can pass to a subset where phi respects all additive quadruples. So namely, phi becomes just usual Freiman homomorphism. And you play that game in each direction. And then what you conclude is that actually phi becomes a Freiman multi-homomorphism on a dense set. So once that happens, you can apply the inverse theorem for Freiman multi-homomorphisms and conclude that phi coincides with some global multi-affine map. And so the remaining of the proof is not very long, but it relies on some important ideas. So first idea is the so-called symmetry argument of Green and Tau, which is important and which allows us to conclude that actually phi is a symmetric map. And also partition rank versus analytic rank plays an important role. But that essentially concludes the proof of the inverse theorem for uniformity norms. All right, so So that was the story about uniformity norms. And we have another application which is quite different. And it's called the multidimensional Bogolyubov argument. So let me start by recalling what the usual Bogolyubov argument is. Is the following very useful statement, which again plays an important role in the proof of Freiman's theorem. So suppose that A is a subset of density delta. So you have a dense subset. And then whenever you take differences twice, so you look at the set 2A minus 2A, you have a subspace of codimension bounded in terms of delta. So basically taking differences gives you very strong additive structure very quickly. So there is a question of how to generalize this argument or this theorem to higher dimensions. And let's think about the case of two variables. So suppose that A is a subset of pairs of G. And then it's reasonable to define the difference set of A in the first direction by simply looking at all horizontal lines. And then for each horizontal line, you take all points that live inside those lines and take differences in X coordinates. So I'm misusing notation here slightly, but you just look at all pairs X, Y, and X prime Y, so the same Y coordinate, and then you take the difference between X's here. So the resulting set is the difference set of A in first direction. And you can do the same thing in the second direction, namely define the difference of A in the second direction by looking at all vertical lines and then subtracting Y coordinates when X coordinates are the same. Okay, and then we have the following theorem called the two-dimensional Bogolyubov argument, which was proved in 2017 by Bienvenu and Le, and independently by Tim and myself. And Hossein and Lovett improved this theorem. They improved bounds to almost perfect bounds in 2018. So suppose that A is a dense subset of the product. And then what we do here is we take the difference set in the first direction, and then we take the difference set in the second direction twice. And then we have another difference set in the first direction 2 times again. And then the conclusion is such a set necessarily contains the best possible structure you can hope for, namely a biaffine variety of bounded codimensions. So what I mean by a biaffine variety, I just mean a set of pairs which solve some biaffine forms being zero equations. So it's just a generalization for two variables of a usual subspace, because subspace is just solution to linear equations. All right, so this is what was known, and we can do the same thing with same definition of different sets in more than 2 dimensions. So this is our second application of inverse theorem for Freiman multi-homomorphisms. And suppose that this time A is a dense subset of the product G1 up to Gk. And then we do the following. So first take the difference set in the first direction, then in the second direction, all the way to K direction. You do the same thing again, first direction, second direction, Kth direction, and you do the whole thing for the third time. And the resulting set necessarily contains best possible structure, namely a multi-affine variety of bounded codimensions. So this time we have solutions to a bounded number of multi-affine equations. And there is one further corollary of this theorem with one-line proof, but it's very neat, so I felt obliged to mention it. So imagine that you have a dense subset with the following property. Imagine that your set is actually a vector space in each principal direction. So what I mean by that, you fix D, and for each D, you fix x1 in G1, xd minus 1 in GD minus 1, xd plus 1 in GD plus 1, xk in GK. And then you consider the set of all YDs such that this whole k tuple lives in X. So this is exactly in the intersection of your set with this particular line in direction D. And if all such lines, all intersections with such lines are subspaces or possibly empty, then you conclude that A once again contains a multi-affine variety of bounded codimension. So what is the one-line proof? Well, just observe that the difference sets do not change your set if your set is already a subspace in each direction. All right, so those were the applications that I wanted to mention. Okay, so I still have some 5 minutes, so let me try saying something about the proof and maybe just stopping in the middle of it if time runs out. So how do we prove the inverse theorem for Freiman multi-homomorphisms? Well, the proof is by induction on K, meaning we assume the inverse theorem for a product of smaller number of vector spaces. And the first step in the proof is actually to generalize this multi-dimensional Bogolyubov argument. So if you think about it, what these difference sets do, well, they're actually convolutions of your set, of the indicator function of your set. So we define convolution in direction D as follows. So you fix axes, all axes except in direction D, and in direction D we actually have the usual convolution. So this is not exactly the usual convolution because usual convolution actually has a minus here and it doesn't conjugate this, but it's essentially convolution. And then the generalization of Bogolyubov's argument is the following. Namely, if you convolve your function sufficient number of times, then the resulting function can be approximated very well using a bounded number of terms of the following shape. So you have a finite linear combination of phases of multi-affine forms. So you have very strongly structured, algebraically structured function here. So there's the first step. The second step is to think about what convolutions do, and it turns out that they generate geometric structure. So what I mean by this is that if you take, for example, if you have two variables and you convolve in directions 1 and 2, this actually counts horizontal parallelograms with 4 vertices in A. So let me draw some things in order to pursue, to be more clear about this. So if you just do convolution in the first direction, what is this? Well, remember that we actually look at horizontal lines with coordinate y. And here we are looking at points on distance w. So we are actually counting horizontal segments of length w. And if you play the same game again in the second direction, what you do is, well, now you're interested in horizontal lines whose coordinates differ by h. And previously we counted segments of length w. So we exactly get horizontal parallelograms of lengths of width w and height h. So with more convolutions, you get more complicated arrangements of points, but still we can control them. And the idea is that the multi-homomorphism, like Freiman homomorphism respected additive quadruples, and additive quadruples were actually just pairs of segments of same length. The same thing happens more generally with multi-homomorphisms. Well, they necessarily respect many pairs of these more general arrangements of points that get same length. So in the third step of the proof, we have a dependent random choice argument, which allows us to pass to a further subset A prime of A, where we do not merely respect many pairs, but we respect almost all pairs. And then we combine this with approximation theorem for mixed convolutions, which I mentioned in the first step. This allows us to go to a situation where we have multi-homomorphism defined on a very dense subset of multi-affine variety. So we cannot get full multi-affine variety, but we can get arbitrarily close to it. And then the rest of the proof is really how do you deal with 99% of a variety. And that's actually the harder part of the proof, a more subtle one, where we have where we apply partition versus analytic rank solution very heavily. And it requires a good understanding of geometric behavior of varieties. Namely, for example, you need to understand what are the sizes of intersections of lines in direction d with your variety. You need to understand that distribution very well. So the fifth step is actually somewhat strange, and we need to understand the biaffine case perfectly, meaning even better than we did in our earlier paper on bi-homomorphisms. So it turns out that we need stronger results of that case in this paper. The sixth step is proving a tool which allows us to use step 5 in the multidimensional case. So we find a way to partition a variety into few pieces so that when you intersect your pieces with planes in principal directions, you get quasi-random biaffine varieties. And the final step is how you actually extend your map. It's actually a two-step argument which we iterate several times. The first part is actually to notice that we have a procedure which allows us to go from 99% to 1 minus arbitrarily small epsilon. And the second thing is actually we can reduce the codimensional variety at a small price, namely going from 1 minus epsilon to, let's say, 1 minus square root of epsilon density. And then you play around and do step 7.b as long as you need to reduce codimension to 0, essentially. So that's basically the sketch of the proof. And I would like to stop here and thank you everyone for your attention.